Okay, so now we're going to have to start the first part of this course. As you'll see, the first almost 2 weeks, we will be talking about integration. I reminded you what integration is and what it does. It calculates areas, and it basically, by the fundamental of calculus, definite integrals basically reduced to indefinite integrals, to so-called antiderivatives. And so what we're going to do is see various methods of integration. And the first method is called substitution. There's a chapter 3 which is called methods of integration, but this is already in chapter 1. And it's a very important one. It's one that we're going to use very much. So it's basically the first go-to way of solving integrals. Now, where does it come from? Before I start explaining it, the method, I want to remind you of the chain rule for derivations. Because that's this, you'll see how it's connected to the substitution. Chain rule for derivations. Okay, let's take a simple example. Let's look at x cubed plus 1 to the power 4. How do you take a derivative of such a thing? Well, of course, what you could do is expand this whole thing, fourth power, binomial theorem, if you still know what that is, and that's a long polynomial, and you take the derivative of that. But that's not really, that's too much work. So what we do to take a derivative, remember the chain rule says you take the derivative of the outside function. This is the fourth power. That is 4 to the power 3. But I don't put x here in the middle. What I put in there is, stop the movie and think about it yourself. Okay, this is how what you can do with these movies. Anytime that I do something and you should be knowing, or I'm telling you what happens now, try to figure out yourself. That way you know whether you understood something or if you said something wrong, then you'll see why it's wrong. Now, so going back, if you now answer 3x squared, that's wrong, because if we take the derivative of the outside function, what we plug in is the inside function, the original inside function. And then, and only then, we multiply with the derivative of that inside function, which is 3x squared. So that's the result. Now, some of you might have seen this or might not have done this. It depends on how you took calc 2, from who was your instructor. But another way of doing this is thinking about the inside function to give this a new name. I'm going to use w. The book always uses u, but there's a good reason that I use w. We'll see later. X cubed plus 1, that's the inside function. Why do I do this? Because, so this is a function f, right? So let's call this f. And so what we were calculating is the derivative of f. But, so what this now says is that the chain rule, another way of thinking of the chain rule is that it is the following: the derivative of f with respect to x is the same as the derivative of f with respect to w times the derivative of w with derivative of x. So if you change the variable, you get this kind of product. And the reason it's a product, it's like gears, right? When you have a gear that is 3 times as fast and you connect it to another gear that is twice as fast, the total result is not 5 times as fast, but 3 times to 6 times as fast. And I'm saying gear because it's velocity, and velocity are derivatives. Okay, but okay, that's not important now. And so, what does this mean then? Well, if we want to calculate df dx, this tells you there's 2 things you have to calculate: df dw. So now you have to write this f in terms of w. But okay, so this was f. What is f in terms of w? So f of w is now just w to the 4th. That's the whole point of the inside function, right? And so the derivative of that is just the power rule. Okay, and what else do we need? We need this guy, dw dx. Well, we have an equation here, and that's also the power rule in this case. dw dx is just 3x squared. And we're done. Because, what does this say? This says df dx is df dw, which is 4w cubed, times dw dx, which is 3x squared. Now, of course, there's a w in here and x in there. There was only, original variable was only x, so we get what w is, we plug back in, and we see that it's 4x cubed plus 1 to the power 3, 3x squared. And that's exactly what I said there. Now I say all this because then it might hopefully understand better now how I'm going to do antiderivatives. It's not really chain rule, but what I'm trying to say is, suppose now that I'm asking you, what is this? What's the antiderivative of this function? Now, if you know that this is the derivative of this function, of this one here, right? Well, then you know that the antiderivative of that function is this x cubed plus 1 over 4. So the answer is x cubed plus 1 over 4, because I've written it here. The derivative of this guy is this guy. So the antiderivative of this guy is this guy. Okay. A lot of underlining here. But if you didn't know that, how are we going to find it? And we'll do exactly the same as we did here using that W. So let me explain it. Let's forget that we knew how to do this, and perhaps let me therefore take a different example. Very similar but different. Let's take W squared plus 1 to the power 5 to WD. Oh, no, W, sorry, I meant x's. Sorry. I meant x's here. X squared plus 1 to x dx. Okay? So I'm going to think the same way. I'm looking for so this substitution here, because that's what we actually were doing, right? We were substituting for W this x cubed plus 1. Okay, so substitution method says you look for an inside function. So W is going to be our inside function. Now that's a bit of a vague concept. It could be different things. Inside really could mean inside some parentheses, but it could also mean, for instance, inside the denominator. It could even mean inside a product. So you have to be a little bit flexible in understanding what inside function means. But it's not the only thing that we need. We also will need the derivative of the inside function. Okay? So let me show you how to solve this problem. The inside function here is clearly x squared plus 1. It's inside the power here. What about the 2x? Well, it's just sitting there, it's a bit separately. Now, so that's step 1. You choose your inside function. Sometimes you make the choice and you see it doesn't work. Let's see, what does it mean it works or doesn't work? Well, the next step you need to do, immediately after you do this, is to calculate dw. The differential of w, or the derivative if you want, that is 2x dx. Okay? And that has to be also, now what we want to do, we want to rewrite this integral, instead of the x variable, we're going to use the w variable. Now remember, it's this dx here that sounds like a silly thing that is just at the end there, and very often people forget to write it. But it's a very important indication. It tells us what the variable is. It's a bit similar as this notation here, which you call the Leibniz notation, where the dx in the denominator also tells us what is the variable. So this tells us dx is the variable, but I'm now suggesting to use a new variable, w, so that should become dw. How do we do that? Well, we know that dw is 2x dx. So we look for 2x dx. Do we have that? And yes, we are very lucky. Here is 2x dx. It's not always going to be that pretty, but almost that pretty. So we are now able to replace everything. Let's use some colors. W is x squared plus 1. So we have this x squared that now becomes w. So the integral becomes w, and it's still to the 5th power. What about the 2x dx? Well, that's something else. That is coming from this guy here. That's exactly this dw, so dw. Okay? And now, see, let's write it in black, then you'll see better what it is perhaps. It's a simple integral. The variable is now w. Doesn't always have to be x, right? We have seen derivatives with t, but now, okay, it's w. What do? How do you derive this? Power rule. Add 1 to the exponent divided by exponent plus c. Is this the final answer? Well, I started with a function that has an x in there, so I kind of would like to have an answer with that same variable. But that's not a big deal, right? So I just have to plug this in here. Remember, it's exactly the same thing we needed to do here, right? We had this formula, but we needed to plug in still. Okay, so we do that. We have x squared plus 1 to the power 6 divided by 6 plus c. And that's the answer. And again, you can now easily check that if you take the derivative of this function, you get this whole inside part here. Sorry, this is this whole inside thing. What we call the integrand, the thing that we needed to integrate. And how do you verify that from there you get that? It's actually exactly the chain rule. There's no accident that verification of this substitution is exactly chain rule. So it's kind of an anti-chain rule that we're using. Okay, that's it. Now, it's not always that pretty, so let me give you another example. Suppose we have to do the following. X radical x squared plus 3 dx. Let me make it here plus 9. Now, there are things that people sometimes think make life easy, and that is distributing radicals, for instance. That is a very easy thing to say, especially when you see all perfect squares. Oh, I know, this is equal to, I'm going to do in red because it's wrong. They're saying, oh, the radical distributes of the s squared, so the radical of x squared is x, and the radical of 9 is 3. That's it. No. If that would be this simple, you wouldn't spend so many hours and hours in 1275 or whatever it is you took to deal with all these radicals and so. No, a radical, there's very little you can do with radicals as sums, okay? So what needs to be done here? Well, nothing. We cannot simplify this. We cannot do anything to integrate this. Sometimes we have seen cases where we write a radical as a particular rational power. You say, that should I perhaps do, but sure, let's write it. One more right now, that's okay. So what would the power be? A half, right? But still that doesn't help us. You could say, oh, I distribute. No, but the problem is this half here. It's the same thing as the radical, and the radical, it doesn't go through this sum. There's nothing you can do with that. So that doesn't work. What do we need to do? Well, it's exactly substitution, right? So let's look. If I do substitution, what should be my inside function? Well, the inside function is clearly x squared plus 9 in this case, right? Okay, great. And that was step 1. If I choose one, the next step I do is calculating the differential, the derivative. So that's 2x dx. So now I look for 2x dx. Oei, I only have x dx, not 2x dx. Is that a big deal? In general, of course, if this w would not fit, then you're in bad shape. That's why substitution often doesn't work. I'll give you examples later. But this fits almost, except for this factor 2. Now, that's the one thing we don't have to worry about, because factors we can always factor out of integral, right? So I prefer to do it this way. I say, okay, I'm going to solve for what I have. Now, notice the way it's written in front here. So it's this x dx. I have to take these two guys together. So you have to get used to the fact that you can move around things, right, with multiplication. So that gives you, so the x dx, I have 2x dx, so I'm going to divide both sides by 2. And now I can replace the green part by the dw over 2. So let's see what we get. So, as I said, the green part is dw over 2 now. I write over 2 there, but it's really 1/2 times dw. Fractions. In principle, the dx should be, or the dw should be always all the way in the back, but we sometimes just lazy and write it as part of a fraction. What is about the rest? Well, the rest, okay, let's go red now again. Rest, that was w. What was x squared plus 9? And that is this guy. And it is to a certain power, a half. Okay, so let's work this out. What do we do with the half in the denominator? The 2 in the denominator? Well, you factor it out. That's the whole point that we're talking about, is that it doesn't matter factors when we integrate. So then we have this thing. Again, that's a power rule, and that is, I hope that you know what to do. Add 1 to the exponent, divide by the exponent. Let's see. And I've already told you I am not interested in simplifications. You can leave it like that. There's no need. You could flip the 3 halves over and becomes 2/3 and cancel what to do, blah, blah, blah. I'm not caring for that. But what I care about is that you have to give your answer using the original variable, which was x in this case. So in other words, the w is not acceptable here. We have to replace it by x squared plus 9 to the power 3/2 plus constant. All right? Okay, so let's do a few more examples. Let's do examples where we have a little bit more complicated functions, like this here. So what's the inside function here? Again, so far insight functions are rather obvious, and we will deal later with more complicated things, but then you have to prepare for that to see this. But okay, so let's do this one. Hold on. It was red, right? My insight function, so step 1, that is going to be the x cubed, right? That's inside. Not sine x cubed, that's too much. I want really something inside. Once I do this, I need to say what dw is. I'll do that in green. dw is 3x squared dx, the power rule of differentiation. Don't confuse both. Okay, so now we look for x squared dx. We have an x squared dx. So we have it exactly what we need. If we don't have an x squared, if we would have x to the 5th, we are stuck. Or x to the 4th, anything, it had to be the right power. It doesn't have to be 3x squared. That's the only thing. And that because I can easily divide here by 3. And now I can replace this. So this x squared dx, the green part, becomes dw over 3. And then what is left? And of course, now everything else should be also in terms of w. There should be nothing else left here. That is this. But luckily that can be done because we have sine of x cubed, which is sine of w. And this is now easy to enter derive, right? Again, the 3 is just a constant, can come out. And the sine is cosine w. Is it cosine? No, it's minus cosine, right? So I put a minus sign here. Plus c. And then last step, important, is that replace w with the original expression. As simple as that. So let me show you what can go wrong. So suppose what I do this here. X squared sine x cubed plus 4x dx. You say, well, this should be working too. Come on, the derivative of x cubed is x squared. I see it. Come on, what are you talking about? I'm going to do it. I'm not listening to you. I'm going to do w is the inside function x cubed plus 4x. That's a 4. Sorry about the Sticklish. This is a 4 here, okay? dw is 3x squared plus 4. The 3x squared, I have an x squared dx, and the plus 4. And the plus 4. Well, what about the plus 4? You say, oh, that's just a constant. It's a plus. It's not a factor, it's a term. So we don't have 3x squared plus 4. We don't even have, we have x squared dx. The 3 we could factor out, but we're still stuck with the 4 here. There is no extra term here that we can use. So that doesn't work. So this is not solvable, at least not with substitution. In fact, I think this is, you have to get used to that many integrals cannot be solved. Although they exist, they cannot be solved. It's not, and it's not because we're stupid, it's just that's the nature of things. Many things cannot be done because it's a very complicated technique, procedure. Okay, so this doesn't work. So another example why this doesn't work. Okay, so I do x squared sine x cubed. Okay, that we could do. And then I'm going to do cosine x dx. Okay. Oh, I like it because root of sine is cosine, so I'm going to do things like that. But now, what could be the inside function be? Well, I would still suggest x cubed, right? And that's step 1. Then dw is 3x squared dx. X squared dx, see, no problem. I know now that I can divide by 3. X squared dx. And so let's replace everything. So this is now, the green part is dw over 3. And now the red part, sorry, I should have done this in red, I guess, is sine of w, that's this, and oh, cosine. Okay, I just write cosine. So this is no. It's a no. You cannot do this. What is wrong here is a w variable, and that's correct because we're integrating w, but this is an x variable. No, that's not allowed. You cannot mix variables. We are doing one variable calculus only. We can only have one variable here. So you cannot replace this cosine. That's the problem. And therefore, this again doesn't work. Again, an integral that is going to be very hard to solve. Okay, there's a couple of examples where things could go wrong. Okay, let's look at some more examples where things can go right. I do one more. Sometimes they can be even nastier or look nastier, but this is okay. What's the inside function here? Well, it's inside, there's no parenthesis here, but inside, obviously, it is the, sorry, I was going to do this always in red, so I keep forgetting that. The exponent, right, sine x. So what is the w then? Or that should I do in green, I guess, okay. The w is then derivative of sine is cosine x dx, and that's exactly what I have. So here we are in a situation that we have exactly the derivative of the inside function. So this is the idea. You have to have an inside function inside something, and then everything else that's outside should be the derivative of that inside function. If there is more here, you're in trouble. If there is not enough, like here, because we need 3x squared plus 4, we only need an x squared or 3x squared, doesn't matter, but if it's not enough, it doesn't work. It has to be exactly what we need, up to a constant, up to this constant that we had here, right? The 3 was not a big deal, that was a factor. But here everything works, so let's work it out. So we get, that is dw, and then we have e and e to the w, right? Because w is sine x. And the derivative of EW is just EW, and then if I antiderive EW, if I plug in back in, that is E sine x plus a constant. And that's it. Okay? So here is an example, some examples. I'll do one more. It's a bit strange one, tangent x dx. Now I'm cheating a little bit, and we'll discuss this in a couple of days, again, this particular integral. Because like this, it doesn't look like an inside function at all. There is a substitution problem at all, because there's no inside function. But that is, if I rewrite tangent x, how do you rewrite tangent x? Sine x over cosine x, right? dx. Now, let's look at this integral. That's a little bit more. Well, okay, we have something, we have a denominator or a numerator. What's the inside part? The denominator or the numerator? That's a little bit tricky. I'm going to give you an example where it's the other way around. Here it's often, as I said, not always, often it is the denominator, so the bottom. So step 1, I'm going to take w to be cosine x. Why? Because step 2 gives me the right thing. The derivative of cosine is minus sine x dx. What about the minus? But that's just a constant. It's minus 1, right? So this tells me that minus w is sine x dx, and that's exactly what we have here. Okay? All right, so I can plug everything in. Let's see. The sine x dx, we said, is minus dw, right? Don't forget the minus sign. And then we have the cosine in the denominator, 1 over w. So the minus sign can come out as any other constant. And then the derivative of 1 over w, you could write this as w to the power negative 1 and think about the power rule, but it doesn't work, right? The power rule. This is a special case. So never forget that there's one special case in the derivative for power rule, that is 1 over w, that is actually ln. So minus ln of w. And then you can replace this minus ln by w was cosine x. We will come back to this and I'll say a little bit more about this particular case. So, okay, but you say, what about if I would say, take the numerator? So I'm going to do this in blue, but you'll see it won't work. I say w is sine x, because you know why I'm thinking that, you tell me? Because if I take dw, I get cosine x dx, and then I have that too, right? It's here. Yeah, but you cannot just write circles like that. You have to be a bit careful. It's not cosine x dx. If what you circled here is dx divided by cosine x, it's in the denominator. That's not the same. So they don't match. So that doesn't work. Okay? But there are examples. Here's an example. Let's look at this one. Okay, try this one. So yeah, you have to practice these things. You have to try these things yourself. So stop the movie, work it out, and then once you're stuck or you think you have something, go see what I do. Okay? All right, so what is it? Well, the inside function here, it could have been x, but it doesn't work because the derivative of x is just 1 and I have ln x. Remember, everything outside has to be the derivative of the inside function. So here, my inside function is going to be ln x. It's actually the numerator. Why? Because if I take the derivative of this, I get 1 over x dx. Now that's exactly this part. Now the dx is in, x is in the denominator. Notice that dx can never be in the denominator. It can never be to a higher power or anything like that. Dx is always dx, just on its own, okay? And then you could multiply it with whatever else you have in the part of the function. So now we can substitute everything because ln x is just w, and dx over x is dw. Look at that, that's a simple one. That is w squared over 2 plus a constant, and then w was ln x. So ln x to the power 2 over 2 plus a constant. There you go. Okay? I want to do one more example, and the rest is for homeworks and so. What about if we have definite integrals? So yeah, I'll do here an example. Let's do this one here. X, I don't know, I'm going to take... Yeah, let's take 3x square root x squared minus 4 between 0 and 2 dx. Okay, let's look at this one. There are two ways you can do now. You could say, okay, I know that by the fundamental theorem of calculus, I have to find the antiderivative and then plug in the endpoints and blah, blah, blah. Sure. And you can do this. So in other words, you do first the antiderivative, and then at very, very end, you plug everything in. But there's a little bit of a shortcut. Let me show you. Well, first of all, we have to solve the integral, even the indefinite integral. What will be the inside function? So step 1, my inside function is x squared minus 4. Because if I, step 2, if I now take the derivative, or the differential, I get 2x dx. Oh, it's 3x dx. Well, that's even worse. Well, not really. I need a 3 there instead of a 2, so what do you do? Well, multiply both sides with 3 and divide them by 2. Right? In other words, multiply both sides with 3 halves. So I do this here. So I multiply with 3 halves, and I multiply with 3 halves. So the 2's cancel, and I get 3 halves dw. I should do this in green, right? Okay, let me do this in green. To stick a little bit to the colors that I'm using. So that is 3 over 2w is 3x dx. That's one way. Another way of doing that is you could also just say dw over 2 is x dx, right? So that is by, again, starting from this here, you just solve, and then you plug in x dx. Oh, sorry. You put in x dx, and the 3 you just keep as part of the integral. The 3 can be, in fact, you could have factored out the 3. So whatever you do it, let me stick to this choice here. So that means here this 3x dx is 3 over 2w, okay, and then this radical will be radical of w. But there's now a step 3 here, or step 2 bis, to step 2b, step 2 prime, is, well, what does this mean here, this 0 and 2? This means x equals 0 for x going from 0 to 2, right? That's the dx is the variable. But if I change my variable in a w, then these endpoints will change, right? If x is 0, what is w then? Well, how do you find it out? Well, here's the function, right? Plug this in here. If x is 0, then you see that w is negative 4. Oh, sorry, I apologize. I was doing something that is not possible. I'm sorry. Sorry. Let me make this into a plus. Otherwise, I run into problems. I'm sorry. I picked this just randomly, but I should have taken a plus here. Let's put a plus here. Okay. If x is 0, then w is, well, 4. Okay, good. And I'll go from 0 to 3. Okay, sorry about that. So this is the integral I'm going to do. I changed my integral slightly, but you see nothing really changes. Okay, now, so the endpoint x is 3. What is w then? Well, w is then 9, no, I don't know why I did 3. I shouldn't have changed that. Okay, I did it now. Okay, I don't know. I was thinking about something else. What is the new value now? Well, you plug it in here. 3 squared plus 4. That's 13, right? Okie dokie. So that's the new endpoint. So what does this now mean? That this integral, after substitution, let's plug everything in. The w, the green part is, we see that here, is 3 over 2w. Okay, so 3w over 2. I'll see, I write it a bit as a fraction. That takes care of my green part here, right? So now the radical. So the radical we do is always in radical of w. That's this one here, right? But now we have also, and I'll do it in another color, these endpoints. And so 0 to 0 corresponds 4, and to 3 corresponds 13. So these become the new endpoints. Okay? Good. So this is now the integral. So, okay, it's a lot of colors. You get so a bit too colorful almost. So let's work it out. So step 3, of course, is now working out the new integral, right? I never said that. But so let's write it out what I have. Well, the 3 halves I can take out. And then I have a radical of w, but we need to integrate, so we need to write this as a power 1/2, dw, and then endpoints are 4 and 13. Okay, so I get 3 halves, the power rule, add 1 to the exponent, divide by the exponent, and then, because it's definite integral, you put in the endpoints at the end. Now, these are the correct endpoints for the w variable. You cannot plug in 0 and 3 here, because these are the endpoints for the x variable. If you want to use 0 and 3, the original ones, you have to first go to the x variable. But I don't need to do this now. I can immediately plug everything in. It's 3 halves, well, 3 halves divided by 3 halves, that cancels out, I guess. So I get 13 to the power 3 halves. That's plugging in this endpoint, and then subtracting 4 to the power 3 halves. That's the answer. You can work this out or simplify this slightly, but I'm not care. As I said, I'm not care about that. So that's the answer. Okay? And that's the advantage, is that you don't have to rewrite back what w is. Now, that might sound a small advantage, but it's sometimes, it really pays off sometimes, and especially later we'll see other things, types of substitution where it works better. So, but that's one way. The other way is just doing what you could also have done. So alternatively, we do exactly the same. So we are at this point here, we have found that this is the antiderivative. Right, so we have calculated the antiderivative, but now the indefinite integral. So let me write up, what was it? 3x, okay, 3x squared x squared plus 4 dx is equal to, so this is where we were. And then you say, oh, okay, w was x squared plus 4, so 3 over half x squared plus 4 to the power 3 halves divided by 3 halves. Okay, that's the antiderivative. And now the definite integral, so that was from 0 to 3x x squared plus 4 dx. Well, that is this antiderivative, and then you plug in the endpoints. Which endpoints? Well, the x endpoints. What are the x endpoints? Well, 0 and 3. Now you might say, this is going to give me something totally different. No, it doesn't. Well, the 3 halves cancel, so that's gone. If you plug in 3, I get 9 plus 4, that is 13 to the power 3 halves. And I plug in 0, subtract, then I get 4 to the power 3 halves. Exactly what I had there. I'm doing the same thing and do it just up at different places. But it's a slightly, this one is slightly shorter. Okay? So I'm going to leave you now to do homework problems. It's a very important method. So do not continue with the rest of the course until you have a good solid grasp on this method here, that you'll be able to do the homework problems. So remember, I'm going to always assign 2 special problems that I want you to try especially. And because these 2 problems, I choose them a little bit because there's some technicalities sometimes, some a little bit slightly more difficult, but they're not really the hardest ones. And then I post a video with the solutions of these homeworks so that you can double check your answer against the solutions. Of course, you can always check your answers at the back of the book. There are also solutions, at least to the odd number questions, so you can also look there. But that just gives you the answer. Here on the videos, I show you the whole the whole work. And work is very important here, right? So let me remind you, on any test, the answer is, for me, really not so important. For me, is the work that you show, all the steps. And I need to see all the steps. I'm going to repeat this many, many times, but showing all the steps is the only way for you to get credit. Just giving me the answer no credit for that, because there are so many ways that you could get this using outside tools, illegal tools that you're not supposed to be using. Remember, you pledged that you will not use anything other than your own mind and your own work and the notes and the lectures. So homework, try as much as we can, do especially the 2 problems, check with the homework video, and then at the end, when you have done all this, remember what you need to do is then self-assess yourself. That is, you go to Blackboard, go to the particular homework rubric, they're listed there, click on it and give yourself as many stars as you think you deserve. And it explains there how you give the stars. I explained this in a different video, okay? And remember, I don't care whether you put 1 star there or 4 stars. I'm not going to look at that. What I'm looking at is that you actually did it. The moment you have 1 star means you have done it. You have done your homeworks. And that's for me the only thing that matters. That's how you acquire this knowledge, acquire the skills, see what the problems are, learn from your mistakes, all this. So it's really not important that you solved homework problems wrong. What is important is that you realize they were wrong, and now you know where you were wrong, and that now you know how to do it. That's what matters, right? And on the quiz, of course, there I would like you to be right. But that's quizzes. And again, we will have reviews for quizzes as well. Okay, so this is for substitution, and for homeworks then, that I will look at the website for the assignments.